Okay, so let's chit chat about the big kind of compilation thing from yesterday. So let me kind of point out some things where this might go south. So generally, there's more trouble on the naming side than there is on writing the formula side, okay? But let's say, for example, you have like number 15, okay? So in number 15, you've got disulfur trioxide, okay? And on any ones that you name, I'm not going to get weird, okay? At most, I might go to 4, okay? That's like, as far as like the prefixes go, most I'm going to go to 4. Probably going to die, try something like that. Here's from my perspective, what's more important that I want to make sure that you understand. Is that the reason that we have to name, and I promise you I'm going to ask you this question. I promise you I'm going to ask you this question, okay? It's going to something like this. I'm going to say, why do you have to use prefixes when naming compounds that involve 2 nonmetals, but you don't have to use them when you have ionic compounds? Okay, I'm going to ask you some version of this, okay? And here's what I hope you understand, is that when nonmetals form bonds, like this, you have sulfur and oxygen, okay? Their difference in electronegativities are very small, so they don't form ions, so there's no oxidation states to add up to equal to 0. So because they're sharing electrons, they can combine in different ratios, okay? That's why you have to use prefixes, because nitrogen, or in this case sulfur and oxygen, can combine in different ratios, depending upon the structure, which is a whole branch of science in and of itself. So do not make this complicated. Do not overthink this. Miles, prefix di means what?
2.
2. So this is going to be S2, okay, sit. And then tri means 3. So it's S2O3. Okay, that's it. I've seen this done. Do not do this. Don't sit there and go, oh, di means, so don't do this. Go, oh, that's 2, and that's 3, and then I'm going to cross that over and go S3O2. Okay, don't do that. Don't. Okay, beg of you, don't. This isn't oxidation states because they're sharing electrons and it's a covalent bond. Okay, so whatever that prefix is, that becomes that subscript down here. That's it. Okay, do not make this complicated. So now on the back side, let's say that you have on number 16 on the back side, you have N2O3. Okay, now here's the deal. You look at N2O3, first off, recognize this and understand the vocabulary. Is N2O3 a binary compound? Luke, is N2O3 a binary compound?
Yes.
Yes, why?
Because they're both nonmetals.
No.
Because they...
Bi means how many?
2. Oh. There's 2.
It's 2 elements, right? Okay. Whenever you have 2 elements, either it's an ionic or it's a molecular. So you have 2 nonmetals, right? You have nitrogen and you have oxygen. They're sharing their electrons, right? So when you write this, okay, you're going to use prefixes. But listen to me. Listen to me, listen to me, listen to me. You are only going to use prefixes when and only when you have 2 nonmetals. That's it. It's the only time. Okay, that's it. That's it. So, Grace, how'd you name N2O3?
N2O3 dinitrogen trioxide.
Perfect. It's dinitrogen trioxide. Okay? Perfect. Wonderful. Could not be better. Okay? Now, if you compare that with something like number 2 up at the top. Number 2 up at the top, you have Li2O. Okay? Now, here's what you're tempted to do. You're tempted to be in this mindset like, oh man, I got these prefixes, right? That's dilithium oxide, which sounds cool, okay? It's like something out of Star Trek. Fire up the dilithium oxide, crystals, and we'll go to warp speed, okay? Why do I not need to call that dilithium oxide? It sounds cooler, okay? It's way cooler on the coolness scale. Why do I not need to call that dilithium oxide? Keaton.
Lithium, the metal.
Yeah. So how many combinations of lithium and oxygen can I have? One, because the oxidation states have to add up to equal to 0. If I have lithium, wants to get rid of its electron, it's going to form a cation. Oxygen over there, it's an anion, it wants to take in an electron. Okay? It's a match made in chemical heaven. So this is just lithium oxide, because that's the only possible combination that can exist. That's it. There's nothing else, because if you do this reverse cross step, the lithium goes up here. There's only one oxygen. That's why it's lithium oxide, because the oxidation states have to add up equal to 0, which isn't true on N2O3 because you're not forming ions, because you're just sharing the electrons. Okay? So that's one of the most important things that you have to understand. Not just the rules, but why we have the rules. Okay. Now, let's talk about number 27 on that back side. So you have FeNO3, 3. Okay? So, what do you know about iron? Is iron one of those that has more than one oxidation state?
Yes.
Yes. Okay? Iron, copper, okay, those are going to be the big ones, and manganese. Those three, iron, copper, manganese. Those are the three that I'm going to expect you to know for that test. So, is this right? Oh, there's one iron. I'm going to write that as iron 1 nitrate. That's an option. I can write it as iron trinitrate, which sounds cooler. I can call it iron 3 trinitrate. Or I can just call it plain old iron 3 nitrate. So which one's right? Why?
Because
You're right. Why are you right?
Because iron needs to take in electrons, so 3 would go into it, and then NO3 just nitrate.
Yeah. Why don't I need to call it trinitrate? Why don't I need to put the 3 in there? That tri.
Because it's an ionic bond.
Yeah, it's an ionic bond. There's only one combination, okay? So stop. Don't do that. Don't do anything like that. Now, what's wrong with calling it iron 1 nitrate? There's one iron. Seems right. Seems rational. Iron 1 nitrate.
There's 3. The oxidation state is 3.
Does the Roman numeral indicate the oxidation state or the number of atoms? Mr. Grill.
Oxidation state.
Yeah, okay, it indicates the oxidation state. If you write iron 1 nitrate, I'm thinking iron has a charge of 1 plus, which it doesn't, because it's either 2 plus or 3 plus. Okay? Now, 21, 22, H2SO4. These are the 2 acids I'm going to expect you to know for tomorrow. H2SO4 is which acid?
Sulfuric.
Sulfuric. HCl is hydrochloric. Okay? Those are the 2 that I'm going to expect you to know for the test tomorrow. Sulfuric, hydrochloric. Okay? Those are the ones. Boom. There you go. Now, let's talk about 13. So number 13, I gave you FeSO4. Okay? Same thought process. So when you have this, is it just iron 1 sulfate? Grace, you shake your head no, and thank God you did. Why?
So you don't need to put the 1 2.
Oh, yes, I do.
You don't?
I got to have Roman numerals.
You do?
I have to have Roman numerals. Because iron, copper, manganese. Anytime you write that name, you have to have Roman numerals. Okay, I have to have a Roman numeral. Anytime. Anytime you name anything with iron, copper, manganese, there is no exceptions. You have to have a Roman numeral. Okay? So here's your options. It's either iron 1 sulfate, or it's iron 2 sulfate, or it's iron 3 sulfate. Those are your options. Iron 1, iron 2, iron 3. Which one can it not be? 1. It can't be iron 1 because iron is either 2 plus or 3 plus. So when you name iron, you got a 50-50 shot. It's either iron 2 or it's iron 3. That's it. Okay? It's not going to be iron 1, it's not going to be iron 4, it's either going to be iron 2 or it's going to be iron 3. That's it. So, Raman, which one is it?
2.
Why? You're right, but why are you right?
Because the oxidation state on sulfate is 2.
Okay, now keep in mind tomorrow, you are going to have a periodic table. You have to know that sulfate is SO4 2 minus. You have to know that. Okay, if you're not, you're dead in the water right from the get-go. If you don't know those 10 polyatomic ions and their charges, you are dead in the water. Okay, I'm going to tell you that straight up. So sulfate is 2 minus. Because they're in a 1-to-1 ratio, iron has to be what? 2 plus. So Raman is right. It's going to be iron 2 sulfate. Now, here's how you can check that you got this right. Okay?
Math.
Take the name and see if you can write the formula. If you start with iron 2 sulfate and you can work backwards to FeSO4, hey, odds are you did it right. Okay? Odds are you did it right. Now, if you had written iron 1 sulfate, let's say you made a horrible misjudgment. And you're, oh, that's iron 1 sulfate. If you try and reverse that process and you go Fe1 plus and SO4 2 minus, and you move that 2, and you don't end up back at the same formula. So that's how you can check when you're naming them, you got them right. I'm more worried about the naming side of this than I am the writing the formula side of it. That's what I have nightmares about. Okay? It's the naming side of this test. (32). What do you have for that one? Hydrogen peroxide. Okay, if you ever had a cut or an infection or something like that, pour it on there, it bubbles up, it's kind of cool. Any ones you want me to go over? Any ones you're thinking, maybe this is right, maybe it isn't? Any at all? Miles,
18.
on which side?
The backside.
Where you have the NH4
Yeah.
okay? So you've got this huge monstrosity, NH4 Cr2O7. Now, here's what you're tempted to do. Don't do this. This is what you're tempted to do. Do not do what I'm about to do. You don't just sit there and go, oh, that's nitrogen and hydrogen. Those are nonmetals. Oh, I got 2 of those. That's ammonia. I'll call this diammonium. And then I got 2 chromiums, dichromium. And then I got 7 oxygens, heptaoxide. Okay? If you have to write out some big jacked up name like that, it's wrong. Okay? I'm telling you, it's wrong. Okay? So here's the deal. Is this a binary molecular compound?
No,
No. Why?
because there's more than 2.
There is so many more than 2. Oh my God. You got chromiums, oxygen, nitrogen, hydrogen. It's a hodgepodge. Okay? So right away, don't use prefixes. This is an ionic compound. What's the name of NH4? Ammonium. Cr2O7. Cr2O7 is dichromate. I would not expect you to know the formula for dichromate because that's not one of the 10. Okay? So all this is ammonium dichromate. It's an orangish salt. Okay? It looks like salt, but it's orange. Got a little cosmo thing. Okay? Any other ones at all you might have an inkling of a question on?
16 on the front page.
16 on what? On the front? Where you have lithium hydrogen carbonate? Okay? So here's the deal. You have 2 versions of carbonate. you have CO3 2 minus, and that's just a straight carbonate. So what this means is that this combination of carbon, you have carbon and surrounded by 3 oxygens, this whole thing wants to take in 2 electrons. So if it's just carbonate, it's CO3 2 minus. Take AP chemistry, we spend a lot of time talking about this. It's a weak acid, so it really wants to take in hydronium ions, okay? So straight CO3 is 2 minus. If you have HCO3, which is 1 minus, so what's happened is that this hydrogen came along and it gave one of the electrons to the carbonate. So the hydrogen comes along and says, hey, you're too short, I'll help you out, okay? It's like the little freshman that owes $2 to the cafeteria and he can't buy lunch. So you walk to him and say, hey buddy, you're $2 short, I'll help you out, I'll give you $1. He still owes $1, okay? But you helped him out. But now you have a bond with the freshman, okay? I don't recommend that, but let's just say hypothetically. So this is hydrogen carbonate. Okay, so the only difference is you put the hydrogen in front of it. But then you knock the oxidation state down by 1 because this hydrogen gave it an electron. So you went from 2 minus to 1 minus. Okay, gave it an electron. So that lithium hydrogen carbonate, so the lithium is 1 plus, the hydrogen carbonate is 1 minus. Swap them out, they're in a 1-to-1 ratio, easy peasy, lemon squeezy, LiHCO3. That's all there is to it. Okay? Do not make that one complicated. Grace.
Part D on 21.
Part D on 21? What's wrong with this?
Parentheses.
So I've given you MgCl2, and we're going to try and name this thing magnesium dichloride.
No, part D.
Oh, the ALOH.
Okay, sorry, no, if you need help, no, you can do it.
Okay? Well, while we're here, let's talk about this. Let's talk about this. Let's chit-chat. So first off, Luke, is magnesium chloride a binary compound?
Yes.
Yes. But is it a compound formed by 2 nonmetals?
No.
No. It's formed by a metal and a...
Non-metal.
So what type of bond is it going to form? Ionic or covalent?
Ionic.
Ionic, because it's going to transfer electrons, right? The chlorine's going to go, yo, son, give me the electrons. Okay? Magnesium says, hey, I got these 2 annoying little twin electrons that are out there on the side. Okay? Eddie and Ernie, the electrons, I want to get rid of them so I can be cool. Okay? So it's a match made in electron heaven. So, why do I not need to put the dye in there? There's 2 chlorines. Why do I not need to put the dye?
It's ionic bond.
So what does that mean?
You don't need prefixes.
Why not? That's the fundamental question. How many possible combinations can I have of magnesium and chlorine? I can only have one possible combination so that the sum of the oxidation numbers add up to equal to 0. So that's why there's no need to put the dye, because I can't have magnesium trichloride. I can't have dimagnesium heptachloride. Okay? I can only have magnesium chloride. That's why it's redundant to put the dye in there. Okay, so let's talk about ALOH3. So here's the deal. What's the oxidation state of aluminum? Find aluminum on the periodic. This is what you've got to be able to do. This is what you have to be able to do. Listen to me, people. You have to be able to do this.
Phosphate.
Aluminum's over there, first column on the P sublevel.
Phosphate.
So aluminum has how many valence electrons? 3. So what's going to be the oxidation state of aluminum?
3.
3 plus. Okay? You have to be able to do this without hesitation. Okay? Aluminum, 3 plus. Boom, here you go. So aluminum is 3 plus. Now, what's OH? What's the name of that polyatomic ion called OH? Hydroxide. So you have aluminum hydroxide, right? So if you write it like this, what does it look like you have? It looks like you have one aluminum and you have one oxygen and you have 3 hydrogens. Is that what I need? No. What do I need? I need parentheses to indicate that I have 3 hydroxide groups and just not 3 hydrogens. Okay? Most common mistake that's made. Mark my words. Okay? If I give you this, say, write aluminum hydroxide, and you put AlOH, then you put the 3, and you don't put the brackets. So amongst the little things that you need to focus on writing those with hydroxides, and realize if you have more than one, you put the brackets. Now, this is equally wrong. Let's say that you have lithium hydroxide, okay, LiOH. Don't put the brackets around there. Why? Because you only put the brackets if you have more than one of those. And if you only have one hydroxide, it's just LiOH. Don't put the brackets unless you're going to put a subscript out there. Okay? Got that one. Anything else at all? Anything going once? How about chromium 3-phosphate? What do you have for that one? Ramen. Chromium 3-phosphate, number 9 on the front.
CrPO4.
Fantastic. Why? There's 3 and 3.
Well, you gotta cancel them out.
Oh, yeah. Chromium 3-phosphate, CrPO4. That's it. Okay? Yay, girl. What?
You do 8 on the front side.
On the front side, where you have 10,2 silicate?
Yes.
Okay? So if you notice, hold on.
Please.
Okay? So right here, you have silicate. Okay? So, and silicate is one of the weird ones. I do not expect you to know the formula name for silicate. It's pretty weird. It's not used all that often unless you're making sand. So you have SiO3 2-. Okay? It's polyatomic anion. So then you've got 10,2. So that's going to be Sn with a charge of 2+. Silicate is 2-. So what do you end up with? Yeah, it's just Sn SiO3. That's it. There you go. Easy peasy, lemon squeezy. Anything else? Going once, going twice, sold. So here's the deal. If you're done with that and you want to hand it in, I'll have it graded and you can pick it up before school tomorrow if you want to use that to make sure that you got it right. If you want to do that and take a picture of it with your phone so you have that, that's cool. If you just want to hold on to it and hand it in tomorrow before the test, I'm cool with that too. Okay? But if you can do that and understand the theory behind it, you'll be in good shape. Okay? But, okay, here's my concern. This is why I lose sleep. You have to realize what you have available to you. Okay? Tomorrow on the test, you're going to have this periodic table. Okay? Now the cool thing about it, it shows you like, oh, here calcium is +2. So if you look very carefully, it shows you what the oxidation states are. Okay? You really don't need to know that, oh, calcium is in group 2, therefore it's going to have two valence of 2 electrons. Over here, oh, oxygen is 2-, fluorine is 4-, aluminum is 3+. So this periodic table gives you the charges on all of your monoatomic cations and your monoatomic anions as well. Okay? Now, but when you get to manganese, for example, manganese has all these possible oxidation states. Same thing with iron, 2+, 3+. Okay? But if you find like silver, silver is only 1+. So this is what you're going to have. Okay? My fear is when it's going to come with those polyatomic anions. Do you know that sulfate is SO4 2-? Do you know that carbonate is CO3 2-? Do you know that hydrogen carbonate is HCO3? Okay? That's my fear. Okay? I'm not worried about the theory part of it. Oh, yeah, why is lithium chloride LiCO? Oh, lithium gives away an electron, fluorine takes one, so one possible combination. I'm not worried about that. Okay? What I'm worried about is if I say, hey, you know, Grace, I'm gonna ask you to write the formula for, iron 3 sulfate, okay? And my fear is Grace gonna go, oh, I got Fe3 plus, and is Grace gonna remember that sulfate is SO4 2 minus? Because if she doesn't remember that, we're dead in the water right from the get-go, okay? Doesn't make any difference at all. So she's gonna go, oh, that's gonna go here, that's gonna go here, Fe2, SO4, 3. That's the easy part, okay? But you have to know that sulfate is 2 minus. If you don't know that that sulfate is 2 minus, we're stopped right there, okay? That's what you have to watch out for, okay? That's my theory. Now, what's the difference between iron 3 sulfate and iron 2 sulfide versus sulfite? So you can have sulfide, sulfite, and sulfate. So sulfide is what? What'd you say, Raman?
Oxygen.
Yeah. Ites and eights have oxygens. This is just sulfide. So you're going to find the element sulfur, just like oxygen is 2 minus. Hey, look, sulfur's in the same group. It has 6 valence electrons. And the other thing I promise you, most likely, I'm going to ask you, why does oxygen have an oxidation state of 2 minus? And do not just tell me it gains 2 electrons. Okay? Tell me why it gains 2 electrons. Okay? So iron 2 sulfide, Fe2 plus, sulfur is 2 minus. This is just Fes. Got it? Good, Grant? Any questions? Going once, going twice, sold. Got it. Okay. So stop yonder camera. Okay, so there's kind of 2 distinct parts to this lab. The first part's kind of fun. And you don't have to have everybody in your lab group do this. So what we're going to study is percent composition. So here's a short version of percent composition. So let's say that I want to calculate the percentage of people in this room that are wearing a black sweater or black hoodie today. Okay? So I want to calculate the percentage of people that are wearing something black. Okay? How would you do that?
Take the total number of people and divide it by the total number of people that are wearing black.
Okay, so in this room right now, there are 13 people. Okay? There are 13 people, well, 14 if you count me. 14 people, right? In this room. So we have 1, 2, 3, 4, 5, 6, 7. Okay? So we have 7 people that are wearing something black or dark in color. So what's the percent composition of people wearing black?
50%.
50%, right? Okay? So percent composition is part divided by whole. Sit. Okay? So here's what we're going to try and do. This is horribly non-scientific, but you'll get the idea. So you're going to take a piece of gum, take it out of the wrapper. You're going to find the mass of the gum before you put it in your mouth and before you start to chew it. Okay? Now, as you chew it, you break down, right? And basically, gum tastes nice because it releases sugar. Okay? Gum that releases vinegar wouldn't sell very well. Okay? But there's a finite amount of sugar that's in the gum. Okay? It's a limited amount. You just can't chew it all day, because if you chew gum long enough, what happens?
You die.
Well, that happens with anything. It's like, if I walk long enough, what happens? I die. Okay? If you live long enough, what happens? You die.
There's no more.
That's a bit touchy when you get to my age. Okay, Ethan, so let's leave the dying part out of this, okay? Okay, it's a little sensitive right now,
You're
okay?
not even that old, you're like 54, aren't you?
56, thanks for rounding. Okay, so here's the deal. So, if you chew long
It
enough,
loses
gum long
its
enough, it
flavor.
loses its flavor. Why?
How's the sugar?
All the sugar is
Oh,
gone,
okay.
right? Sugar is gone. So basically what we're going to do is we're going to start with a chunk of gum, and we're going to find the mass of it, right? Okay? And then you're going to chew it, right? Okay? And eventually, you're going to chew it long enough, kind of till that flavor goes away. Then, and let's say that that's, I'm going to make up a number, 2 grams. Okay? Let's just say your initial mass is 2 grams. And you're going to chew it, okay? And then you're going to weigh it afterwards, and let's say it shrinks down to 1.8 grams. Okay? Now, here's what you want to be very careful of. Okay? You started with 2 grams, you chew it, you're down to 1.8 grams. Okay? How much sugar did you lose?
10%.
No, just mass. How much sugar was there in the gum?
0.2 grams.
0.2. So what you did is that you took the total minus what you have left, right? Which got you 0.2. So it's total minus what you have left means that you had 0.2 grams of sugar. Okay? Now, how am I going to find the percentage of sugar in the gum? Take 0.2 and divide it by total. Now, what we just did is we just came up with an algorithm. Okay, an algorithm is a thought process. Okay? So you took the total mass that you started with, right? You subtracted what you have left over, right? And then you end up with what you lost. So the difference in what you started and what you ended up with is what you lost. Cool?
Yep.
Then you need to take that and divide that by the total. And then to get a percentage, what's your last step? What do you do with that? After you take 0.2 and divide it by 2, what do you do? To get it as a percentage, multiply by
100.
100. Okay? So you got that idea. Now, this is where this gets a little bit disjointed. What else? So when you begin to chew it, what else is going to mix in with the gum?
Saliva.
Saliva. So to really do this right, and we don't have time, to really do it right, you'd actually chew it, dry it out, then find the mass of it afterwards. So we're not getting a true representation of the amount of sugar, but we're doing this just so you get an idea of the process. Okay? So go in there, as soon as you get in there, before you get in there, take it out of the wrapper, find the mass of it. And I just need a couple of people in each group to do this. Not, if everybody wants to chew gum, that's cool. Okay? I'll leave it up to you. Just don't, like when you get done, just don't stick it underneath lab tables. Poor form. Okay? Horrible form. So that's kind of the pre-lab part of it. Now, when you get to the actual lab part, okay, lab part itself, the technical part, is going to deal with hydrated salts. If you're hydrated, what does that mean? You have sufficient amounts of water, right? So you're going to have, for example, down here, you're going to have hydrated calcium chloride. So hydrated calcium chloride, and the formulas are written on there on the labels. So calcium chloride is ClCO2, and then there's a dot, and then there's 2H2O. Okay, so let me explain how you read this. So what this says is that you have an ionic compound of calcium chloride. And what's happened is that there are 2 water molecules that have become bound to this. Now, these are not water. These are not liquids. Don't look at this and go, oh, this is like a solution. Okay? It's not. You look at it and it's just, oh, CaCO, it just looks like a normal salt. But there's water that's bound to it. So here's what you're going to do. You're going to take a test tube and find the mass of that empty test tube. Okay? It's one number that you're going to need. So you're going to take a test tube. Make sure it has a white spot on it, and all of them should, because we're going to heat this up. So you're going to find, and this is data that you need to record. So back here on this other side, you need to set up and think through this and go, oh, hey, what data that we need to record? You need mass of just the empty test tube. You're going to end up with 3 different test tubes. Mass of the empty test tube. Boom, boom, boom. Put it on the scale. Easy. Then you're going to add between 2 to 3 grams, for example, of the calcium chloride. Okay? So you're going to add that until the mass increases by about 2 to 3 grams. Okay? So you're going to have the mass of the empty test tube. Okay? Then you're gonna have the test tube plus the hydrated salt, okay? So that's gonna go up by about 2 grams. If you want to do this, you can just set the test tube off, take a little weighing dish, put it up there on the scale, re-zero it, just like you've done before, add 2.5, whatever mass you have, pour that in there, and then you can add the mass of the test tube plus the hydrated salt to get the total mass, okay? That's the simple part. Now, what you're gonna do next is you're gonna fire up your Bunsen burner, okay? You're gonna do not hold this thing in your hand because you're gonna get this thing really hot. So here's the test tube, and you're gonna hold it in the test tube clamps, okay? Make sure that they are pretty tight on there. If your test tube clamps are loose, let me know, I'll get you another pair. And you're going to heat that test tube in that. So you're going to put heat into the system. So what you should see is that as you're breaking those bonds between the water and the calcium chloride, you're putting energy into the system. Because remember, this is kind of going to go full circle. Remember when we talked about melting ice and boiling water and things like that? Okay? Remember, to break bonds, you have to put energy into the system. So you're going to heat this up, and you're going to break those bonds that hold the calcium chloride to the water. The water molecules are going to be, at this point, superheated. They are like on steroids. Okay? They are like, woo! We're out of here. And they're going to leave. Because they're like, fine, you don't want us, we're out. Calcium chloride's going to be stuck behind because you're not going to break the bonds with the calcium and chlorine because those are really strong ionic bonds. The bonds with water molecules are pretty weak. So that's why we can heat it up. So what you're going to do is that you're going to see probably little bits of moisture begin to form on the end of that test tube. What you want to do then is heat up then the end of that test tube so that you drive that water completely out. So heat this, and it's going to vary, probably heat it like maybe a couple of minutes. So here's what's going to happen. You're going to heat this up, you're going to heat off the water's going to go away. Very similar to the idea of what happened with the gum, okay? Oh, instead of mechanically breaking down your gum and that sugar being absorbed into your body, we're going to heat it up, break the bonds that hold the water. The water says, we're out of here, the calcium chloride is left behind. So the technical name of what's left behind is anhydrous calcium chloride. So hydrated is what you have before. The anhydrous is what you have left over, okay? So basically, you're going to heat this thing up, heat it up. You're not going to heat this up for like 10 minutes. You're going to heat it up for a couple minutes, okay? Not a big deal. If you really want to get fancy and to do this right, what you're going to do is you're going to heat it up for a couple of minutes. Then you're going to take your stirring rod and you're going to kind of crush that salt up that's left behind. Kind of crush that up and mix it up a little bit and then heat it again, okay? And then just to make sure that you get all of that water out of there. So then when you get done, you're going to put it back on the scale. So you're going to have basically the mass of the empty test tube. You're going to have the mass of the salt. You're going to have the mass of the test tube and the salt. And then you're going to have the mass after you got heated up. So you need 4 bits of data for all 3 salts, okay? So on here, you've got copper 2 sulfate, calcium chloride, sodium sulfate. When you get in there, when you look at the bottles, it's going to say this is what it is. Now, one of the things it's going to ask you to do is name these. So calcium chloride is CaCO2.2H2O. So if you name that, that's calcium chloride. Now we have 2 waters. What's the prefix for 2? Di. So this is calcium chloride dihydrate. If there were 3 waters, we would call it trihydrate. Okay. If there was 1 water, it would be monohydrate. Okay. So it's going to be the name of the ionic compound, a prefix that indicates the number, and then hydrate. Okay? So the copper 2 sulfate That's gonna be CuSO, so it's gonna be copper sulfate. And let's say there's 5 waters. So that would be copper sulfate pentahydrate, okay? So here, this is where your data table is gonna be. You want 4 masses for all 3 salts. So you're gonna have a total of 12 bits of data that you need to put in here. Yes, because you're my students, I give you additional questions, call it tough love, but it is. So this one, you've got some questions that you need to answer. Oddly enough, there's some mole conversions, question about which direction the heat energy is flowing, that type of thing. So here's what you don't want to do. I'm done. You have to work quickly. So even within this, we got a bunch of people going today. So work together as a group. So let's do this. Just in case we need to combine, share data. Ellie, your group, you start with the copper 2 sulfate. You guys do the calcium chloride. What's left?
Sodium sulfate.
Sodium sulfate. Okay? Get those. At a minimum, get those done. If you have time, then do the other ones. But at least that way I know we're going to have data for all 3 groups. So when we run out of time, we can compare data. I'm just doing that as a buffer, just in case you don't have time. You should have time, but this is just in case because it's Wednesday. That way I know we're going to have data from all 3 hydrated salts. Okay? Let's go.